Welcome everyone to our second Van Horn lecture series. The Van Horn lecture series is always fun for the faculty, and I hope for our distinguished lecturer. Each year we reserve blue skies and fine Cleveland weather for this week. But the real purpose for this lecture series is for you guys back there, our graduate students, to interact with distinguished scientists and find out that they are real people. Now, today's lecture, Professor Cedar will use the term ab-initio. Ab-initio is from the Latin, ab meaning from, initio meaning the beginning or the start. I was surprised to find that this is actually a rather old legal term from like the 1600s. In English contract law, a contract was found to be void ab initio, meaning from the very beginning it was never going to work. Now, having usurped this legal term, give that a minute to sink in, scientists use it to mean first principle calculations that do not depend on external parameters except the atomic numbers of the constituent atoms to be simulated. An interesting evolution of the term. Now, Professor de Geer yesterday provided an excellent introduction to Professor Cedar's remarkably productive career, but where did it begin for you graduate students back there? We should examine ab initio, Professor Cedar's publication record, and it starts here. In this paper, Monte Carlo simulations of oxygen ordering in YBCO. This paper, for those of you who want to do the math, was published in 1989, and I'm sorry, but that was 30 years ago. And in 1989, some interesting things were happening, besides the fact that Professor Cedar published one of his first papers. For instance, the Berlin Wall fell. That was a historical moment. The first 24 satellites of the GPS system were sent into orbit. And there was culture in 1989. Hard to believe. Rain Man and a fish called Wanda won at the Oscars. More importantly, the first episodes of The Simpsons aired.
Wow.
Nintendo released the Game Boy. Microsoft released Office. Where would we be without that? More importantly, to work in simulations, Intel released a 486 microprocessor. It operated with a clock speed of 50 megahertz. That was outstanding because it was just 8 years earlier that the IBM PC was released with an 8088 with a clock speed of 4.77 megahertz. All our graduate work coming back to us. Now you can buy a computer with 8-core system with a clock speed of about 5 gigahertz, pretty inexpensively. That's a 1000x increase. Now, we're all familiar with Monte Carlo simulations. They rely on some random walk. And here's a trivia question for you. What is the topic of Albert Einstein's PhD thesis? Brownian motion. Very good. In fact, in his seminal year of 1905, 2 of his papers were on Brownian motion. His thesis was on determination of molecular dimensions, and his paper on Brownian motion. In fact, Brownian motion was described by Robert Brown in 1828. It's in the Edinburgh New Philosophical Journal, which is all digital. You can go read those on the web. And so it's 77 years between the experimental observation of Brownian motion and Einstein's description of the random walk process. Altogether, Einstein publishes 5 papers on Brownian motion, which are summarized in this very nice book. My favorite one to quote is from his 1908 paper. Professor Lorentz called to my attention in a verbal communication that an elementary theory of Brownian motion be welcomed by a number of chemists. Acting on this invitation, I present in the following a simple theory of this phenomenon. Apparently the tension between chemists and physicists go back a little bit longer than I thought. Now in these papers he develops a relationship such as the root mean squared displacement and the Stokes-Einstein relationship that describes diffusion coefficients. And in our graduate courses and our courses we teach in diffusion, we use Monte Carlo simulations to simulate the random walk. These are termed kinetic Monte Carlo. What was different about Professor Ceder's paper is they used the Metropolis Monte Carlo, which is to simulate a thermodynamic ensemble and calculate the energy of it to determine which state had the minimization of the system. In other words, he didn't use simulations to model experimental results, but rather used simulations to predict equilibrium and non-equilibrium states. And it's really remarkable that 460 publications later, give or take a few, Professor Ceder has new tools and new methods, but the same ambition. Very interesting to me. To use simulations to predict equilibrium and non-equilibrium states of matter. And so, if you would, from Ab-initio, your presentation today.
Great.
Thank you very much.
This is a picture taken every few years. We take a retreat. We go away for 3 days. This one is in Lake Tahoe. Usually we have a lot of fun, and we discuss. It's prepared. People discuss a lot of things, but the only thing we don't talk about is about the research we do, like now. So it's all about what we might do and we're cool. So one of our topics was actually electric aircraft. And so this picture is taken by our drone. We bought a drone, we played with it, and then like good engineers, we took it apart. And so that is the first drone we ever had in the group. So if you want to find where Case Western is and you don't know where it is, right? What do? You use Google Maps, and you know you can plan routes. I mean, you have enormous amount of detail. Now, actually, Google even has integrated the plans of some buildings, right, that are public. And if some buildings you zoom in, you'll actually see the corridors and everything, which is remarkable. So that's what you do when you drive, right? So what do you do when you do material science, right? Your maps are a little older and a little less complete, right? Material science is sort of more like this situation where I don't know if you even recognize where this is, right? This is actually the east coast of the United States. This is kind of Newfoundland, right? This is Labrador, Newfoundland. This is Florida. Isn't quite to scale, isn't quite in the right place. And I think this is Long Island here, right? And then, of course, there's all the parts you don't know. There be dragons, right? So material science, instead of Google Maps, is a little more like this. And in the old days of the materials genome, I sort of thought I'm going to quantify it at once. And this is not a scientific quantification, really. But I looked through a bunch of books like Landell Bernstein and so on to see how much data do we really have about materials, right? Because we like to say we do things rationally, so based on data. So, and I want to put it in perspective. If you look at the number of inorganic crystalline compounds we know today, it's somewhere on the order of 10 to the 5th. It's sort of 50,000 to 200,000, depending on how you're counting. So how much do we know about them, right? It's a good question. We act like we know everything about compounds. Well, if you want to know the elastic constant tensor, 200 compounds. I mean, we know a few more bulk moduli and Young's moduli, but actually the full tensor, 200 compounds. And I may be off by 50 or 100, but that makes it 300, right? You know, the best known property is TC, because it's been measured over and over again on compounds. It's pretty easy to measure. So TC is known for about 1,000 compounds, superconducting transition temperature. The dielectric constant is known for about order 400-500 materials now. And you think that'd be pretty easy, right? Measuring the dielectric constant. The full piezoelectric tensor, I mean, that is like, you know, that's worth gold, right? That is almost not, never known. That's about 50 compounds. And so, you know, unless you do trivial properties, we're almost always below 1% in coverage across. And you know, the argument sometimes is maybe we know all the important materials. All these that we don't know are not important. Well, you know, I can show you some counterexamples if you want to bring me to it of how we missed important materials by not knowing the properties. So imagine that you kind of knew everything, right? That you know the basic properties of every known compound, that you would know the band gap and effective masses, Seebeck coefficients, electron mobilities, whatever you want, that you would know the full elastic tensor, the dielectric constants, maybe absorption spectra, point defect energies, right, solubilities, the electronic signature of those point defects. And then if you're into mechanics, maybe you want to know the stacking fault energies, the parallel dislocation barriers, and things like that, right? So, maybe if you're into nucleation, you want to know surface energies in air, in aqueous environments, and so, and that you had the capability to query these upon request. I hope you agree with me that if you had this, you would develop a much more quantitative theory of material science. Because our problem today, the reason is our field is terrible at being you know, we're very good at qualitative relation building, but we're not very quantifiable, and that's because we often don't have the numbers to put into our theories. And I think what I'm going to paint you the picture that we're actually not that far from this, because every property on this list is actually computable today. It is actually computable by ab-initio methods. We just don't always do it. Sometimes it's still hard. Sometimes there are accuracy issues. Sometimes we just don't want to bother doing it for thousands of compounds, but there's not anything on this list here that we don't know how to compute today. So that was actually our vision in the sort of mid-2000s when I was still at MIT, is, you know, we thought these are not engineering properties, but these are the basic intrinsic properties of compounds, right? And out of compound properties, you build engineering properties. And engineering properties are much harder to calculate, but we felt if you could sort of catalog the basic intrinsic properties of compounds, that was the genes of material science. And if we could quantify all that, we'd call that the materials genome. And lots of people got upset by calling it a genome because it's not hereditary and all this stuff. And once I was in an elevator coming out of a building where I just given a talk, and a woman goes to me and says, "You're the guy from the Human Genome Project, right?" And I said, "Right, half of the time, but not human genome." But okay, so one of the reasons we can do this is because of ab-initio computing. And I want to sort of maybe continue my thread that I did yesterday of how a bit of basic science can go a long way, in this case 100 years. You know, sort of, if you think of the beginning of the 20th century, Niels Bohr, you know, the structure of the atom, 26, Schrödinger formulates essentially his wave equation idea for quantum mechanics. Then it took a long time of messing around. And then essentially in 1964, Hornberg and Kohn, that's misspelled, that's Kohn, recast the Schrödinger equation, which was really the elegant idea that they recast this as a density functional, that if you just wanted the ground state energy, you could solve this as a density functional problem. But as a good classic physicist always does, they prove to you that the problem is exactly solvable, but then say, but you can't really do it. So, and that was sort of where Hornberg and Kohn left us. 1965, just a year later, the Kohn-Sham equations were developed out of the Hornberg-Kohn theorem, and they're the ones we essentially still solve today. Then, you know, come the 1980s, I'm about to finish high school here, or college, sorry. And you know, DFT starts being applied to simple elements. People do silicon. Copper is really hard at the time because it sort of has full D states. And the machinery of today's DFT is being developed. Pseudopotentials, right? One of the great inventions for making DFT practical. Things like the local density approximation, and then later the generalized gradient approximation. So these are the sort of practical approximations that made the density functional theory a practical theory. Because it's not clear that Hornberg and Kohn ever thought this would be a practical theory. You know, then we come mid-2000s. By now there are stable codes. I can tell you that in the 80s there were not stable codes. Actually running something was like, you constantly had to look at whether things converge, and you had to look at things manually. By the mid-2000s we have stable codes that actually work most of the time. So at that point we start thinking of since this works most of the time, computing can be automated, you can do high throughput computing. You just write a bunch of scripts, and instead of doing one calculation, hey, let's do 500 at a time. And then in 2011, the Materials project is launched after it's moved to LBNL. And today, we sort of calculate millions and millions of properties on demand from ab-initio methods. But there really is a direct line, right? We wouldn't be doing this if all this other work in physics hadn't been done. It's really that simple. OK. So the Materials project, again, is not the Materials Genome. Actually, the story that happened after the story is that we talked back and forth with OSTP, the Office of Science and Technology Policy, and they said, we want to launch the Materials Genome Initiative, but there's one thing. You can't use the name anymore, so we renamed ourselves the Materials Project, which was great because we didn't have to argue about genes anymore to people. It sort of started at MIT, but we realized we could never really run it at a university, especially not MIT. So Christine Pearson, who leads it now, moved to LBNL and started it there, moved in 2009 and launched it formally in 2011, and still the director of the Materials Project, and she's the one who's really made this work. It was one of these things that we built, and we didn't know if people would come, right? If you've ever seen the movie, you build it and they'll come. But they came. There are 78,000 registered users of the Materials Project today. There are 1,400 distinct sessions a day. That means distinct people who are doing operations on the Materials Project today. And each day, we exchange 600,000 data items in the Materials Project. So this is real, right? People actually use ab-initio data, and ab-initio data is being used by non-theory people. And that was really our vision, right? Because theory for theory people, that was only going to be so useful. Theory for the broader community is really what we wanted to do. It's about to be launched as a user facility at Lawrence Berkeley Lab, although I think that's actually confidential, so you forgot you heard that. But today you can go on the website and look up stuff, right? And keep in mind, just like Google, everything you read on the internet is not correct. So everything you read on the Materials Project is computed, so it's not necessarily correct. You are still required to use your brain somewhat. You can screen compounds, you can look at formation energies, you can do Pourbaix diagrams, which is things in solution. You can look at crystal structure. There's now a robo-crystallographer, which really, if you haven't tried it, you should try. A robo-crystallographer, you take a crystal structure and it describes it to you in words the way a solid-state chemist would do. It says these are corner sharing octahedra or phase sharing. It's actually pretty cool. It's sort of data mined on the way people really talk. So I've always wanted this because I stare at pictures and I go like, I don't get it. Is this like phase sharing? Is this corner sharing? Is like, okay. You can look at band structures, calculated diffraction patterns. There's now quite a lot of compounds have phonons, and you can visualize the phonons, which is kind of cool, especially for teaching. There is now a lot of absorption data being added to the Materials Project. There are tons of elastic constants. There are about 13,000 full tensors now. You can do lattice matching. You can look for substrates to grow things on. There are equations of state. You can look for structure similarity. This is actually a quite useful thing. Very often you have a compound you like, but you want something in a similar structure, or you want something in a related chemistry in a similar structure. So there's all these similarity metrics that you can use. There are dielectric tensors. There's piezoelectricity on it. OK. So, but I want to sort of pause a bit and tell you where this all came from, because it's actually a good story, and it's a story of serendipity. In the early 2000s, I had a postdoc, Dane Morgan, and Dane and I sat around and said, everybody says all this computing thing, this ab-initio computing is kind of valuable, and the question was, so we said, well, can we really derive value from it? We should just prove it. So we started a company, and that was called Computational Modeling Consultants. And the whole idea was like, well, if it's valuable, somebody should pay for it, right? And we had a few customers, and actually one of the first ones was Energizer here out of Cleveland. And Energizer made us work a little on alkaline batteries, right? But of course their competition noticed that because we published a paper on it, and so Duracell came along. and said, we have bigger work for you. And there was a dinner with some executives at the top of the hub. And one of the executives was sort of like, just knew enough science to be dangerous, not a whole lot. She was a statistician, actually. And so she goes like, oh, I hear you calculate battery materials. And she goes, can you calculate everything? And this is one of these moments where you go like, you could say, let me think about that and get back to you in 3 weeks, right? Instead, we sort of went, yeah, I think we can. And then she goes like, how much is it going to cost? And I go like, 1.2 million. I had no idea what I just said, right? But what I realized is that, if I come back in 3 weeks with a full proposal, they're going to send it to their board and this and that, and nothing will ever happen. And so basically within weeks, it's probably more like 6 weeks or so, we had a signed contract from Duracell. We couldn't do this within MIT. This had to happen way too fast. We had to do this within a year. So we got a band of people together. We didn't quite do it in our garage. It's a more complicated story. And then we forgot we needed computing because we were going to do high throughput computing. We actually didn't have computers. So we went back to Duracell and said, Duracell at the time was owned by Procter & Gamble out of Cincinnati, right? They're now spin out. And we go like, damn, we need more money because we need to buy computing time. And they, of course, didn't want to give us more money. So they go like, but we just built this giant computer center in Cincinnati, and they don't have any work yet. Because they felt the future was in simulation, but they didn't have anything to simulate yet. So we called them up, and they're so happy we're calling them. We were worried that we're going to steal their computer time, but it turns out we validated them because suddenly they had work, and we got basically a year free access to all the computing power in Procter & Gamble, which was great. Okay, so here's what we did. This was the first time we did high throughput computing. So everything got patched together, lots of scripts being written. We started with 130,000 compounds, calculated voltage that they would have in discharge in an alkaline environment, capacity, energy density, and stability turns out to be the hardest. Because if you ever open up an alkaline battery, there's a reason it's called alkaline. It's pH like 14, 15. It's basic KOH with a drop of water in it. So it corrodes everything. So what we learned is very quickly that all these other things didn't matter. It was all about whether the material could be stable in high KOH. And it turns out that was by far the biggest screening thing, that there were only a few oxides that were ever going to be stable in high KOH. So we filed a bunch of patents together with Duracell. They were all bismuth 5 and nickel 4 containing compounds. And the really cool thing is that they are actually launching a product this summer. So this summer, when you go to your supermarket, there is going to be, I can't tell you the name yet of the product because branding is so important for them. There is going to be a new battery, which I'm sure they're going to charge an awful lot of money for to pay back for that $1 million. But you will see a new battery. It's going to look like the copper top, but with a cooler design. And it is based on one of these new compounds. They, of course, had to do a ton of engineering, but it was in some sense the first materials genome compound. Okay, after that, we go like, well, this is good, right? We should do more of this. We did another one with another company, which never wanted to be named. And then OSTP got word of this, and that led to the Materials Genome Initiative in 2011, which was a clever name because when I talked to Tom Khalil, who ran that part of OSTP at the time, he says, Gerd, please don't call it the High Performance Computing Initiative because nobody will give you money. But if you talk to the Congress and you call it the Materials Genome Initiative, they think that's really cool. And it's about materials, it's about genomes, it has all the right ingredients in it, and we're going to fund it. So if you work in Washington, right, nobody knows any science, keep that in mind, especially when you go, the higher you go up on the hill, the less science people know. So it needs to sound really cool. So in 2011, the Materials Project is launched. In 2012, it's actually funded by the Materials Genome, and we're sort of off to the races. So that's a bit the history. What I want to do first is show you a few examples of materials design, and then if I don't talk too much, I'm going to show you about where the future is, the problems we have to solve. So sometimes you find materials just by looking for them by high throughput screening. And here's an example where, this is from Christine Pearson's work, for auxetic materials. So auxetic materials are things with a negative Poisson ratio, but in all directions, right? So negative Poisson ratio is kind of cool, right? Normally, when you pull on something, it shrinks in the other direction. In a negative Poisson ratio, it actually expands in the other direction. And if you can do that in all directions, there's some interesting applications you can use. Actually, it's used in sound dampening tools, for example. And if you look at known compounds for which the properties are known, like the Poisson ratios are known, this is the distribution of the Poisson coefficient. And of course, it's around a third. It peaks because that's the most common Poisson ratio. But there's actually one material in here. You can't even see it. It's because there's only one material, and it's silicon dioxide in the alpha cristobalite structure. So they wanted to find more of these. So what they do is they take these structural motifs, because what gives it a negative Poisson ratio is the fact that you have all these hinges in the structure that can rotate. And they look for other materials. They do a big screening. They look for the motif. And then at the lowest tier, where they only retain a few structures, they actually do density functional theory. And they came out with a bunch new ones. Well, a bunch being like 1, 2, 3, 4, right? But so we went from 1 to 5. And one interesting one, which some of you may be familiar, is the high temperature polymorph of aluminum phosphate. Is actually an oxidic material, but it's been really hard to verify because you need it sort of either in single crystal form or in the right sort of sintered material form. So this sort of sometimes materials just lie out there ready to be found. And that comes to my first point. There's just a lot of properties we simply don't know about materials. And if you don't have to even invent new materials. You just have to know what the properties of the known materials are. But we also try to discover new compounds. And we do that with a fairly rigorous control technique. So we try to go from the sort of known compound space to novel compounds. And the question is sort of how do you make novel compounds? You just put randomly all elements together. And we essentially do that by data mining chemical knowledge. So what we do is we take the known compound set, which is order sort of 50 to 100,000, and we learn from that chemical substitution. And so this is a matrix of essentially most elements against all other elements. This is actually the cations all. And the color scheme is essentially how easily they substitute for each other, retaining crystal structure. So if we have that information, we can take known compounds and make them in another chemistry. That's really what this does. And just for those of you who know your periodic table well and substitutionability, this is, of course, the lanthanides here, right? They have high substitutionability for each other. This here is the column 2 elements, right? Barium, calcium, strontium. This is the transition metals. And so you generally pick up which elements are substitutional for each other. You don't need to have the right answer. You just need good guesses because in the end you do density functional theory on them. So I want to show you just very quickly a few examples of that in action because now you can just let the computer play. The computer can take known compounds, apply these substitution rules on them, do calculations on them to see if they're actually stable, and then calculate their properties. And you can just let the computer run. So we discovered this battery compound because we wanted vanadium redox couple. This looks like some totally weird chemistry, right? And that came from an iron-containing equivalent. And the computer just realizes it can often substitute iron for vanadium. And then when it calculates, it found that it's actually a ground state. So this compound was not at all known. But the computer basically sort of found it just by using substitution rules. And this student, this is Anubhav Jain, he's a theorist. He was so excited. And he goes like, this is my first compound I ever predicted. And he wanted to make it in the lab. So we trained him. And he actually made it. And here's the diffraction pattern. It was smack on, right? He made it in a week. Works well in a battery. This is a double substitution, a very unusual chemistry. These are carbonophosphates. It's a rare combination that carbonate and phosphate groups are combined. This is a natural mineral. It's called siderenkite. We didn't want to work with sodium at the time. And we did a double substitution, or the computer did one, manganese to iron, sodium to lithium. And again, this is driven by data mined algorithms. And then you calculate its stability. We can now make it with multiple different transition metals. We actually made it in the lab. And you can actually cycle it in a lithium battery. And so these were, again, compounds that were essentially largely independently designed by a computer by us, giving it only a few simple rules to search. Okay, so recently we did this on a much larger scale. We had a project with Center for Next Generation of Materials by Design, which is another acronym that's unpronounceable. is together with NREL, and we were interested in novel nitride semiconductors because nitrides tend to have lower gaps than oxides, so they're a bit more interesting as adsorbers. They are also not as explored as oxides, right? For every one nitride, there are 14 oxides in the ICSD database because people just do a lot more with oxides. So we thought there would be a lot of nitrides you could discover. So we decided to do a giant high throughput search for novel nitrides. So we did binary metal, so ternaries, right? 2 metals, A, B, and nitrogen, and we wanted to see how many new compounds we could find. And so there are 2 problems, right? You first have to find the stable stoichiometries in this ternary phase diagram, and then you have to find what the crystal structure is there. Again, we do that with data mining driven algorithms that drive the density functional theory, right? So the ultimate accuracy is still the one of density functional theory, but the data mining is essentially guiding you to what are the likely stoichiometries and what are the likely crystal structures, and then you calculate their energetics. And so I'm just going to give you the short of it. We studied 900 chemical spaces, right? One chemical space is one choice of this doublet here. And so we found 392 stable ternary nitrides, of which about 200 were known and about 200 were new. So in some sense, overnight here, we've doubled the number of known ternary nitride compounds. Now, you could argue, well, maybe all the new ones we found are wrong, right? Is this sort of possible? So we did a statistical test. Now, statistical test here means making them, right? And so our team at NREL picked 10 of them, and 9 of them were successful, right? So we seem to have very good accuracy in predicting novel compounds and novel ground states. Okay, so I think that computational design of compounds is actually doing quite well, right? We are getting better, we are getting faster, methods are getting better. There are still properties that maybe you cannot predict with good enough accuracy, like band gaps or some electron properties, but it often doesn't totally stop you from doing design with materials, right? You don't always need to know the property super accurately to design, you just need to know it good enough, because in the end you're going to make it and measure it. But the challenge we more and more face is the one that we do not understand what is synthesizable, right? We have no bound on our design space. So if I start putting elements together, where do I stop? How do I know how to bound that space? And that would be even better if I actually not just know what can be synthesized, so I can bound my design space, but also if I could know how to synthesize it. And this is a project that I started with 3 people, but by now it's a project of about 6, 7 people, and the driving force has really been Wenhao Sun, who's about to start a faculty position in Michigan. So again, the challenge is, what we want to answer is what can be made and how can it be made. This is really driven by a need, right? We have designed several compounds that look nothing special, but we can never make them. And they would have tremendous applications. So sodium molybdenum fluorophosphate, this is a known crystal structure. It's known for vanadium. This is actually calculated to be a ground state. I have spent, well, my postdoc and student have spent 6 months in the lab with all kinds of synthesis technique and no sign of life whatsoever. And after 6 months, people give up, right? Because it's sort of a true non-result that is even hard to publish. Lithium zinc diophosphate, this is predicted to be the fastest known lithium-ion conductor. I mentioned that yesterday. This one is crazy. This would be the fastest known magnesium-ion conductor. This would be a magnesium-ion conductor that is as fast as a lithium-ion conductor, which is truly remarkable, right? Because it's a divalent ion. That is a metastable phase predicted, so nobody knows how to make it. Okay, so when you talk about synthesis, right, people sort of go like, well, you do thermodynamics, and this is all kinetic, so you have nothing to tell me, right? And I like to quote Alexander Navratri, who has a perspective on this. Alex has a broad education, and she says in archaeology, when you don't understand something, what you find, you say it must be ceremonial because you have no idea what that. Everything could have been ceremonial, right? So in material science, if you don't understand something, you say it must be kinetically controlled, right? So in our field, kinetics has been this excuse we are allowed to use like we don't have to try. It's kinetics. Okay, let's go on to the next problem. But you know, kinetics obeys the laws of physics, right? There really is something here that we should predict. And the other thing we should never do, we should not orthogonalize to kinetics and thermodynamics. Thermodynamics is really an application of local boundary conditions and looking at equilibrium under these local boundary conditions. And much of kinetics is really just determining what what that locality and those boundary conditions is, and then you have a pseudo-thermodynamic equilibrium. So if you're going to try to study synthesis, you could sort of probably think of a few ways to do this. You could think of like, you know, I'm just going to simulate it, right? I'm going to follow atoms and I'm going to simulate and track dynamics. That's never going to work, right? Because the time scale of material synthesis is just not the right one. The length scale is not the right one. Condensed matter synthesis, unlike organic synthesis, is a collective phenomenon most of the time, phase transformations, whereas in organic synthesis you have sort of unit processes, right? You have, you know, in organic synthesis they know exactly if you have a benzene ring with a hydrogen, how to take the hydrogen off, how to put the metal group up and stuff like that. The other one is you could try to develop theory, and that's what I'm going to talk about today. And what I'm going to talk about tomorrow is the beginnings of another approach, which is a data-centric one, right? Can a computer learn synthesis by reading data? But that's for tomorrow. So if you're bored today, then tomorrow may be more your liking. Okay. So the first thing I want to do is, how did theorists think about synthesizability up to now? And it was all basically determined by energy. We have something that we call the convex energy hull. If you take a binary, what you do is you plot mixing energies, formation energies between A and B as a function of composition. And the lowest envelope is what's called the convex hull. These are the thermodynamically stable phases. And then, like here, delta would be a metastable polymorph, right? It has a bit of energy above the ground state. This would also be a metastable polymorph because it would be metastable against phase separation into alpha and beta. So if you read a theory paper from any theory paper from the last 30 years, and they calculate new phases, they will usually tell you it's so much above the hull, it's on the hull. And what's a good number for synthesizability? That depends on how optimistic you are, right? Like some people say, oh, it's 50 MeV per atom above the hull. Some clever chemists will make it. They never say who the clever chemist is, right? Some people go like, it's 100 MeV. You could still make it, right? So the question is there actually an energy scale of metastability? So today you can do that. You can investigate that because we know how many compounds are observed, right? We have a list of observations, which is the inorganic crystal structure database. And then we can, in high throughput, calculate phase diagrams and enthalpies of formation and mixing. And so we can compare the two. So the question is, how much of the world is metastable? It turns out about 50% of known compounds are metastable. Order of magnitude. It's a bit of a tough criteria to exactly slice, but it's order 50%. Okay, if you look at this across chemistries, and this is definitely not a complete list, so this is the typical energy above the ground state of metastable compounds. And this is the sort of percent, this is the 10 and the 90 percentile. And what you see is a lot of them are sort of, you know, very similar. They kind of reach up to about 100 millielectron volt per atom. If you're a chemist, that's like, 10 kilojoules per mole. I can't do British thermal units, or kilocalories. But of course, then you see nitrites, for example, have much larger metastability, right? And that has to do with the strong covalent nitrogen bond. You can do an interesting analysis whether high component systems are more or less metastable, but I'll let you try to read the paper if you want to figure that out. The answer is actually non-trivial. Okay, so what we roughly figured out was that most metastable compounds are within about 100 millielectron volt above the ground state. Right? What Christine Pearson's group did is to try to come up with a more chemistry-specific limit. And they started with the hypothesis that maybe the amorphous state is an upper limit for metastability, right? And the reasoning roughly goes like, well, a material can always go amorphous if it wants to, right? If it's already in the mixed state, but it can't always crystallize in a structure. So they just wanted to test that. So for a lot of different chemistries, they calculated the energy of the amorphous state, right? And the reason that there are error bars is because you do sampling of the amorphous state. It has many different configurations. And then you put on there the energy of the known polymorphs, stable and metastable. And this result is truly amazing, right? By the way, the solid circles are known polymorphs. The open circles are unknown polymorphs. every single known polymorph is below the amorphous limit. Every single one. There has been not a single exception to that criterion. And what's interesting is this criterion picks up chemistry, right? Look, giant metastability in carbon. This is a discussion we had yesterday, so, right? You know, carbon goes up to 800 millielectron per atom, and that's the buckyball, actually, right? But then there are other things like, you know, boron oxide has barely any metastability. Titanium oxide, vanadium oxide, it has a lot of metastable compounds, but not a large energy range over which they live. Okay, so you think we solved the problem, right? Because we have an energy range now for metastability, so maybe everything in this range can be made by a clever chemist. This clever chemist, which we don't know who he is, but or she is. Okay, then we did this test. You should always quit while you're ahead, right? So we did this test. We took some very well-studied systems, right? You know, titanium oxide, iron oxide, vanadium oxide, and this is the energy of the known polymorphs, right? Like for titanium oxide, you have rutile, brookite, anatase, you know, ramsdellite, et cetera, et cetera. Okay, so then we, in the computer, made up a bunch of other crystal structures. Really, we would take known crystal structure types, but put them in that chemistry, and we calculate their energy. Damn, right? So what it turns out to be that there's a ton of possible crystal structures in this range of what we thought was metastability, 100 millielectron volt per atom. So the known metastable compounds are in that range, but it turns out there's a ton of other ones in that range. So mathematically, what we have here is a sort of required criterion, but not sufficient criterion, right? So yes, metastable crystalline compounds have a fairly low energy range, but there's a ton of other ones that are in that range and nobody ever sees them. And you know, maybe you think that somebody should try harder to see all these weird polymers of TiO2, but I don't think so, right? There are like 20,000 papers on TiO2, order of magnitude. I would be shocked that they would have never observed any of these. So it is more likely that these compounds just can never be made for some reason, even though they have low energy. And so in some sense, the real finding here is that something that has low energy cannot necessarily be made. This is a common error made in theory, right? Sometimes people say it's only 2 MeV above the ground state hull, therefore somebody can make it. The answer might simply be no. There has to be a reaction path and a reaction mechanism to that. And so the question that now follows is, can we predict which phases have reaction mechanisms to them, right? Is sort of the next one. Okay. So that's sort of the next part of my talk. How do you think about what can be made? So we made a hypothesis which is called remnant metastability. And the idea is the following, that if you take some pad between precursors and product, that you know, you go through several different phases of nucleation and growth, and sometimes your environment changes, your chemical potential in your environment may change, your composition may change, your temperature may change. Our idea is that a metastable phase is one that is thermodynamically actually stable in during the conditions of your growth, right? So at some point, maybe your metastable phase is the most stable one as a nucleus, or it is the most stable one under a different composition than the one you started and ended with, and then you retain that phase. And I'll tell you in a second why this is important, right? So the idea is it's still thermodynamics, but it's thermodynamics under different conditions than what you thought it was, okay? And I'm going to give you some examples of that. So I think I just said that. So there clearly, you believe this in part. Even if you think you don't believe this, you have already believed this because you believe in temperature quenching and pressure quenching, right? So I can make a phase at high temperature and quench it down and retain it, and I can make it at high pressure and retain it, right? That I think most of you will agree with. So what we want to do is we want to generalize quenching in other variables, right? That's the whole idea, that these conditions where you make things is not just a matter of temperature and pressure. There are other thermodynamic variables that control your boundary conditions, and under those variables you create the stable state, and then you quench it in some variable space. Okay, so generalized quenching, of course, delta T and delta P, but we obviously know that you can grow things metastably under strain, right? You can do epitaxy and then retain it even if you release the strain. We know that you can create phases at a different composition and then change the composition but retain the crystal structure. That's what is called soft chemistry, or chemie-douce in French, right? You make a crystal structure, you can change, for example, some ions, diffuse them in and out, but you retain the network. And then obviously you can play with size. You can make phases that are stable at the small size, but then as you grow them, you retain them. And anatase is a great example of that, right? Anatase form of TiO2 is stabilized by surface energy. So at the small particle size, it actually is the ground state, but you can actually grow it to quite large particle size and not go to the ground state being rutile. Okay, so our hypothesis is that the set of accessible metastable crystalline phases is essentially the set that lives in this enlarged thermodynamic space. And maybe we didn't catch all the variables, but it's going to be something like this. So if they can exist in this space, then they can be made. If they do not exist in this space, they cannot be made. Okay, so that means that in some sense, we have to figure out how to calculate phase diagrams in this enlarged space, right? And that's a real challenge, but I'm going to show you some examples. Okay, so again, I think these three you believe, right? I'm going to talk mainly about the other ones. So here's, I think, a simple one, the polymorphs of manganese oxide. So MnO2 has a ton of polymorphs, you know, pyrolusite, ramsdellite, hollandite, these kind of integrals. It has bernesite, layered phase, it has spinels, roughly all the same composition, MnO2. So the question is, can you sort of understand that stability? And you can, because they are often grown with alkalis in solution. And if you look at the phase diagrams of pH versus a chemical potential of an alkaline in solution, you actually find that most of these phases, actually all of them, hollandite, bernesite, ramsdellite, actually appear somewhere on these phase diagrams. So the idea is that they are grown, or at least nucleated with the alkali, and then actually continue to grow and the alkali gets oxidized out. Okay, so the one that's maybe more interesting is size. And the reason is that we already, I think, also believe to some extent that size matter because nucleation preference is set at a small size. So, for example, if you look at two nucleation curves, right? This is a classic out of material science. You look at free energy of transformation as a function of the particle size that's transforming or that's forming. And here I've taken a case where green is the stable phase because at large particle size, it has the lowest free energy. But beta has higher free energy in the bulk, but it has a lower nucleation barrier. So in this case, you will form beta first. And if you can keep beta as it grows into the larger phase, you've essentially quenched it in size, right? Just like you quench things in temperature or in pressure space, you quench things in size. And so that means we now have to look at phase stability as a function of particle size. And I'll show you a few examples. The first one I was interested is pyrite versus marcasite, right? Pyrite is the stable form of FeS2. It's called fool's gold, right? Marcasite is kind of an interesting one because it would be a better absorber. It has a better band gap. It's known in nature that marcasite tends to form hydrothermally in acidic environments. And it's also interested because it offers powers of vitality, assertiveness, and confidence. So important material. Okay, so if you actually calculate the energy of these two polymorphs as a function of particle size, this is a lot of work because you have to calculate all the surface facets, you have to do the wolf shape, and worse, we have to calculate with all the possible absorbance, right? If you're in an aqueous environment, you can absorb protons, OH, water, O2. And when you actually do that, you can actually make a phase diagram now as a function of pH and particle size, right? So here you're really small, here you're 1 nanometer, so huge. Here's the pH, and what you see indeed, marcasite is the stable phase at low pH, so in acidic environment, and at small particle size. And that is actually because marcasite has an easier time doing absorption of H3O, so actually protons combined with water. It has a stronger absorption energy of that. So this is very consistent with what people find in nature. I'll show you quickly another example. Calcium carbonate, the stable phase is calcite, right? That's the one you find in minerals. Aragonite is what you mainly find in the ocean, right? The shell of shellfish is mainly formed out of aragonite, and that's actually a metastable phase of calcium carbonate. And it's been known empirically that this is highly correlated to the magnesium content in seawater. Because it's actually to the point where the magnesium content in seawater has historically fluctuated over hundreds of thousands of years. And when it's below a certain point, you actually don't form aragonite in the oceans. And again, that's a surface energy problem. So what happens is in aragonite, calcium is highly coordinated by oxygen, and magnesium does not want to substitute in there. So magnesium has essentially no effect on the surface energy of aragonite. But magnesium does substitute into calcite, because in calcite, calcium is 6-fold coordinated, which magnesium can go into. And magnesium actually increases the surface energy of calcite. So what you see what is happening now is if you go into high magnesium environments, calcite is still the more stable phase, but it actually has the higher nucleation energy because it has a higher surface energy. Again, so this is an idea of thinking of these more enlarged spaces. In some cases, you can get truly complex reaction sequences, and what we're learning is this is actually more common than we thought. This is an old experiment. My students call this old because it's from 1984. I shrug when they say this is old. But also maybe if you see these diffraction films, for those of you who are older, the way people did diffraction, this is an interesting experiment. So this is a manganese 2+ precursor in solution, in aqueous solution, and they just leave it in there. There's nothing changed to it, and they look what happens over months, and they take the diffraction pattern. And here's what happens. So in the beginning, you have a manganese 2+ in solution. The first phase you form is manganese 304 spinel. And if you just let it sit, it forms beta manganese oxyhydroxide, then it forms gamma manganese oxyhydroxide, and then it finally forms MnO2. By the way, if you take a Pourbaix diagram, which is a phase diagram for solutions, right, it should form MnO2. So by here it has actually formed the equilibrium phase, but look, it went to 1, 2, 3 intermediates. And these are well crystallized, right? Look at this is pretty sharp diffraction line. This is not some gooey gunk that formed on the way to the MnO2 formation. This is well-formed crystalline phases. So if you look at the Pourbaix diagram, again, this is, if you don't know Pourbaix, Marcel Pourbaix was this great Belgian, like so many scientists, right? So just kidding. Who developed Pourbaix diagrams, which are phase diagrams in aqueous environments, right? So you have pH on one axis, and then you have potential on the other. And potential, if you're not familiar with this, is essentially a measure of the oxidation ability of your medium. And so the first problem you have is, so we're actually somewhere in here trying to make beta MnO2. So I got a bunch of these phases here. They're not even on the diagram, right? The manganese oxyhydroxides aren't even on the diagram. They're not even stable phase for any condition on this diagram. So it's not like I could end up in the wrong space here. The question is, why do I form these at all? So the first thing to do is to do this quantitatively is sort of build the right thermodynamics, right? And so if you passed your qualifying exam in material science, you know nucleation theory, right? That's sort of the classic question. If you do kinetics, that's the one question they always ask, right? Like nucleation theory. And so what nucleation tells you that there's a critical activation energy for nucleation, which is proportional to the interfacial energy cubed, and then the bulk driving force squared. But the question is, what is this in an aqueous medium? Because in an aqueous medium, you're sort of compositionally unconstrained, right? You put stuff in solution, but how much comes out of solution? It can get oxidized, it can get reduced, it could take more oxygen from the solution, it could take protons from the solution. So it's an open system, so you have to do my favorite topic in the world, thermodynamics. You have to take the Legendre transform of the Gibbs free energy, and that looks really complicated, but really what matters is your Legendre transform with respect to the chemical potential of water, the pH, and some potential, which is again the cost of your electrons, right, to do oxidation reduction. If you do that, you can do really cool stuff, and you can sort of put this now on some kind of map. So this is again the phase diagram, but now you can actually put an energy on it, which is the equivalent of free energy, right? And so this is the stable energy surfaces, but you can actually now put the metastable energy surfaces above there, right? So there are energy surfaces living above the stable convex hull, and you can project this down on the phase diagram. And what you're seeing is that in this region in which I'm playing, they're clearly, the oxyhydroxides are actually very close. So how can I now quantitatively predict the reaction sequence? Okay. So first thing I do, so I'm going to do this. We set up an experiment with people at SLAC where they do this in situ. So in situ, we put manganese 2 plus precursors in solution. We put a certain amount of alkali in, potassium hydroxide, and we want to see the phase sequence that things go through. So I have to understand the phase stability as a function of the amount of potassium, as a function of the pH, and as a function of the size, right? Because I have to study nucleation. So we do all these factors. I'm going to go a little faster. We look at phase stability as a function of potassium content. Then we look at a function of size, and this is really the cool one. Again, this is the bulk phase diagram. Okay, this one I'm going to spend a little more time on because this is now a phase diagram as a function of size. So this is now at a fixed potential because it's a three-dimensional map, so I have to slice it somewhere. This is the pH axis. This is size, bulk here. This is small, right? So this axis is this line here. And what you see in the bulk, okay, you have only manganese 2O3 and beta MnO2. But if you go to smaller size, these other phases start to appear, right? The oxyhydroxides are starting to appear on the diagram. Actually, the spinel appears even though we're not in the bulk phase stability region of the spinel. And so what you're seeing is that these oxyhydroxides could be stabilized just as nucleation preference by size. So you can put all this together in some formalism, right? Size, pH, et cetera, and then we can actually go and see, can we predict what goes on in the experiment? So we work with SLAC, and they did experiments in this phase diagram at a few different chemical potentials of potassium. So when you're very negative, that's essentially almost like no potassium. So what we would predict is that you would start with Mn2 plus in solution, form bernesite, which is the delta phase, then go to Ramsdellite, and ultimately form the equilibrium beta MnO2. Okay. This is when the music should play, right? So, okay. Lots of cool setup. This took a long time to really make work. Okay, what do they find? Okay, this is what the theory predicts. What they actually find is almost what the theory predicts. They first form delta, which is the bernesite. Then they form gamma, but gamma is essentially a slightly disordered version of Ramsdellite, so I still count it as a 90% win. And then they form beta, beta MnO2, the pyrolusite. So really good. So the phases that form in sequence are essentially the ones predicted by sequential nucleation, right? So this is a case where clearly theory can actually tell you what forms and in what sequence, right? And anytime you would interrupt this, you would make a metastable phase, right? If you say, I'm going to interrupt it here, I would have formed this metastable phase, right? Okay, then I'll show an example that's a little more complicated. So we now go to a higher potassium chemical potential. So now you would expect to go manganese 2 in solution, then you cut into this red region, which is the bernesite, the delta phase. There's a sort of tiny Ramsdellite sliver you might cut through here, the beta phase, and then ultimately the hollandite, which is the alpha MnO2. Instead, what they see is they see the bernesite, so they see the red region form, and then it goes straight to hollandite, right? So now we only see two phases. And what's really happening here, right, is that what's actually happening is that the delta phase forms, and then it grows so fast before the other ones can nucleate, and it goes straight to the alpha. So in some sense, it's not giving the other ones a chance to exert their preference because the size has already grown so much that these are not stabilized by size anymore. And so this is clearly something we cannot predict yet, right? When you have competitive phenomena, right, it could either nucleate, say, beta out of solution, or it could just rapidly grow in size. We cannot predict that competition because that would require that we actually predict all the rate constants for all of this. So we sort of get the sequence, but we can't predict which phases it skipped. So I think with that I'm going to end, right? And I think I started with saying, you know, I think what we thought was going to be the material genome is, I think, remarkably within reach. Today, if somebody can compute something with ab-initio methods, in most cases we can scale it, right? And we can do it over tens of thousands of compounds. And don't underestimate the power of that, right? What we have found is people do things with data that you would not do. And just the fact that this data is available there, you know, people use this in creative ways. And that's, I think, one of the beauties of scaling ab-initio computation. I talked a bit about the issue of predictive synthesis. And one finding of us is that metastability and I stress the limitation here, right? Crystalline inorganic compounds seems to be limited to a fairly low energy range, but the corollary to that is not true, right? Not everything in that energy range seems to be synthesizable. And we are currently working with this hypothesis, and it truly is a hypothesis, right? This is not a theory, that most metastability is what we call remnant metastability, in the sense that it's only metastable because it was stable once in some enlarged thermodynamic space. It is not an accident of nature. Or as somebody at the Gordon conference says, you know, nature is not random, right? Nature does the same thing every time on a sort of macroscopic scale. And I think that lends some strength, I think, to the idea of remnant metastability. Metastable phases are not, you know, crappily little formed nuclei or collections of atoms, right? They are long-ranged, ordered phases. The only way that can happen is if your thermodynamics at that point wants to do that, right? So you have to be almost by definition under a condition of thermodynamics where it wants to make that phase, and that's really the idea that drives remnant metastability. So I think with that I'll end, and I'll be happy to take some questions. Thank you. Art.
I'm really surprised that excellent MnO2 does not appear in your talk.
God, epsilon MnO2. But there's a lot of controversy. I think, if I remember what epsilon is, right?
That's the
It's a disordered one, right?
yeah, this is
Yeah.
defect nickel
Yeah.
arsenide structure. HCP packing of oxygens, and
Yeah.
along the C-axis, vacancies in manganese and
Yeah.
urate. Very common in all the...
Yeah, no, I worked on epsilon MnO2 a long time ago, but I'd forgotten. But is it ever seen out of solution? I thought it...
We studied materials with pure epsilon MnO2, made by the usual process of electrodeposition from a manganese sulfate spar.
Yeah, so we've never seen, well, I should say the SLAC people never saw epsilon MnO2. And we actually, I'm not even sure we calculate it because it's partially disordered.
There's at least 2 ordered polymorphs, which we determine the space groups of using TM. So it's real.
Sounds like I should read your papers again.
I'll give you a copy.
Yeah, I can do that. I think I read them a really long time ago.
John?
So in your data mining for solid state stuff, there's lots of data, it sounds like you can access for temperature dependence of whatever, phases exist and things like that. But in the synthesis side of things, the stress state is often not this kind of stress state. And so do you have to, or can you put in like the equation of state of the material? And does that data exist? So when you're doing things under different pressures plus temperatures, things shift around. In some cases quite a bit. Is that in there now or easy to do?
I mean, so are you asking the question, could we look at nucleation under complex stress state? Is that the question, or is...
Pressure effects on
Yeah.
processing so you can get different phases?
So, as you know, pressure effects on thermodynamics are small in general, right? The P delta V term.
Yep.
I think... So I think stress terms are small, but strain terms are not, right? And this is a subtlety, right? Because like if you do epitaxy, right, you actually have strains that would correspond to really large stresses if you were to do it mechanically, right? Like imagine that you do epitaxy with 2% strain. If you were to do that, if you were to try to do that by elastic deformation, it'd be crazy, right? So strain is an important variable on nucleation. Stress is not.
Say you had a non-cubic system,
Yeah.
just putting pressure on it, which generates strain.
Yeah.
That can be plastic.
Yeah.
So then it becomes important.
So you can include that, right? Because we can calculate the elastic stored energy and how that would differ between the polymers. If you stay within the elastic limit, though, that number is not very large, right? I mean, just because of the units, right? The P delta V term in thermodynamics is not particularly large, and so the elastic strain piece isn't very large either, right?
Mark?
So I love compounds, just like you. We ceramists tend to like compounds, but I'm sure you have some techniques for dealing with non-stoichiometry and solid solutions.
Great point. So we do. A lot of them are not. So small amount of solubility is not a problem, right? That's kind of a single atom point defect model that, you know, if you start talking 1% and below, that's not a problem. But if you're going to true solid solutions, so the techniques for that exist, right? There are things like cluster expansions. The problem with them is that they are not particularly scalable today, in the sense they're not easy to automate, right? We are working on that, and I think that the progress has been tremendous on this, but I think it's maybe a couple years away. So you can do this kind of one at a time. Like, we study solid solutions all the time with Ab-initio, but it's sort of like, you know, 6 months of a student there, right? Trying to build the right cluster expansion, getting the configurational entropy. And the last 5 years has seen a lot of kind of more mathematical development to stabilize that process, because it's largely a convergence problem. And algorithms that have all kinds of quirky convergence problems you cannot automate, right? That's the problem. If it's a human that has to look at it, oh, did this converge, did this not converge, what do I do now? You cannot automate. And that's why you have not seen a lot of solid solution work in kind of a high throughput mode. You can do it in low throughput, no problem. But it's going to come. It's going to come.
Like Arthur's paper is going to come.
I now remember that. Now I'm more embarrassed because I actually remember that I read them like a long time ago.
Actually, you did some calculations?
Yes, I did. I'm really like, you know, I'm starting to feel really old.
About stable currents or stable compound high pressure and then taking the pressure off and quenching it. I think there are a lot of examples where then it goes back.
Yeah.
So what is known and understood about how do you avoid that?
Yeah. So we cannot make a, okay, so to a large extent, we cannot make a statement about the lifetime of metastable states. We simply cannot. So what I've showed you is a theory to tell you what metastable states it gets into. But think about it, right, how hard it is if you wanted to predict the lifetime of a metastable state. So one part of it is easy if it becomes mechanically unstable, like, right, it starts to get imaginary phonon frequencies. That's trivial, right? I mean, you just calculate the phonons and you know it's going to slide off into something else. So that part is easy, but that's really like only 10% of cases. And sometimes in pressure, that is the case, actually. So the pressure variable is maybe a little easier to deal with. But the other variables, the problem we don't know how to do it is sort of competitive nucleation, right? So let's say I make one of these phases, right? Like in manganese oxide. How would I predict that it goes to another one? I would have to calculate either the solid-solid nucleation, right? So when does a new solid nucleate in another one? Or in solution, it could also go by redissolution, reprecipitation, right? So that problem, the solid-solid phase transformation, I think we really don't know how to do in Ab-initio, because the solid interfacial energy is a nightmare, right? It has too many variables to optimize. I think it's one of these things that conceptually you could do. In practice, it's just a giant can of worms. There is stress involved. There is, you know, it's like solid-solid grain boundaries, but now like times 10, right? Because you got a ton of them. You have to chemically equilibrate them. You have to positionally equilibrate them. This is already hard enough, so I'll do this for the next 10 years.
Peter?
So have you looked at the evolution of these different structures in terms of crystallography, in terms of, say, subgroups, supergroup, those type of things?
So there's a team in Christine Pearson's group working on that, because this comes actually to the next question, right? So to the previous question. In some cases, you can predict some of the easy phase transformation pathways, right? And sometimes that has to do with subgroup relations. So we see that there are some phase transformations that happen really fast. And therefore, if you go into the metastable phase, but it has a fast transformation pathway out of it that's lower energy, it's going to be really hard to retain this. And some of that has to do with basic structural relations. So there is a bit of a complex reality out there that maybe I didn't show. But there's actively work being done on that, actually.
Bruce?
When you're discussing the energy, in some ways it reminds one of the end of 19th century and Gibbs. Gibbs realized, of course, that it's not the energy or the enthalpy, but it's the free energy, which is a combination of enthalpy and entropy. And as far as, I'm not sure if I'm right or not, but really Ab-initio calculates the enthalpy and doesn't calculate the entropy part. And the question is how easy it is to calculate the entropy? Is it possible for Ab-initio to,
Yeah.
and how accurate is it?
So we do it, and yeah.
It's so
Yeah.
complicated.
But we do it all the time. We rarely do it in high throughput because it's more work. But so the two dominant components tend to be vibrational and configurational, right? If you have a mixture configuration, if you have a compound, it's really just vibrational. And we know exactly how to do it. It's just a lot more work. And then there's the electronic one in some cases, right? And so we do that when we do more detailed studies. But you got to look at some of the scale of these energetics, right? So some of the scale of these energetics is like hundreds of milli-electron volt. So no entropy is going to like rearrange those that kind of energy scale. But the methodology to do it is quite well known, and it's done quite routinely. Maybe the student should ask a question.
Wonderful idea.
Yeah, the student should ask.
So,
Are you a student?
Yes, he is.
if I'm not, I've got some concerns. So, kind of,
speaks Latin.
I find this E to S. I find this interesting dichotomy. I'm curious as to your thoughts of what comes of that. At the very beginning of the talk, you were talking about something very practical. In fact, you were sitting down with CEOs who would only pay you money, and so far it was practical. And it goes not into a less practical, but more theoretical in terms of synthesis. Can this be synthesized? And are finding kind of limitations of can it in fact be synthesized? But that doesn't necessarily mean it's easy to synthesize, or that's going to be something that per se Energizer wants to do. Of yes, great, you can make this compound with PVD on a very small couple atom thick film, but we don't care about that because that isn't pertinent for our scale of application. So granted, that's a whole other can of worms, as you said, but what would you see as being the steps to get there in terms of adding to or adjusting the models or paradigm that you already have?
To make it, to only look for simple synthesis?
To look for practically implementable, scalable synthesis.
Well, okay, so I have a lot of answers to that question, right? But so a lot of these are scalable, right? So synthesis out of solution is done as an industrial process. Solid state synthesis is done as an industrial process. Epitaxy is done, but not to make like giant quantities of material, right? But the other thing that I've learned, right, is that I've worked with companies to do material scale up, that they are really much better at it than I am. And that when a material is worth it, right, that people get really creative, right? So, you know, that for us, the job is to find interesting compounds that work, be honest about them. And if it's really worth something, like I'll give you an example, like lithium iron phosphate is an interesting example. You know, lithium iron phosphate was supposed to be a cheap compound because it contains iron and phosphate groups, right? How can you go cheaper for the battery industry? Well, it turns out in the beginning of the battery industry, it was the most expensive battery material you could buy by multiple factors. And that's because the precursor that you needed was not a standard iron oxide, you need iron oxalate and stuff like that, which is an expensive precursor. Industry has totally solved that problem by now. Right? So people go and they try all kinds of creative ways. Now you can just use like, you know, run-of-the-mill iron oxide and you can make lithium iron phosphate, and now it is actually a really cheap cathode material. So I think the sort of experience is that, you know, I'm not trying to cop out here, right? But that you shouldn't always limit yourself too much. I mean, you should be aware of these issues, but I don't think you should completely lit yourself, right?
So on that, you showed 3 compounds that your
Yeah.
team has been looking at that you've not abandoned yet after 6 months. But is that one of these situations where better conditions under control, you think you can get there? Because that's what.
So we are looking at these things now, right? So we have a few more of these so that are higher priority, but we're trying to understand for some of these compounds, what route would you take to make them metastably? And that's really all we're trying to do, right? We're trying to give some guidance, sort of like, if you're going to make a metastable compound, can we start to think about how we can predict synthesis routes? And I'm not sure we always have to be exact, right? We just have to be better than like guessing at it, right?
Yes.
So do you ever look at the interface, say the oxide interface, where you have 2 dissimilar materials and what the energetics of
Yeah, so we do. Solid-solid interfaces are hard.
Yes.
and I'll come back to that. So we obviously do solid gas is quite easy, but there's still an equilibration problem because there's crap in the air, right? That there's still a chemical equilibration. You can't just calculate a vacuum interface. And we do solid liquid. Water is actually not that hard because, I mean, the species there are protons, hydroxyls. You only have to equilibrate a few groups with your environment. Solid is really hard for the reasons we mentioned before. And to be honest, sometimes we do a back of the envelope calculation where we just throw in it's 1 joule per meter squared, which is a classic interfacial energy, right? And you sometimes show that stuff will not happen at all at that kind of interface, or will happen. And you do a sort of sensitivity analysis. Well, what if it's 2 joules per meter squared, or what if it's or a half, right? And you go like, well, I'm sort of in the range where it will always happen, so I don't really care. And then you don't have to do all this enormous amount of work to calculate the solid-solid interface, which is not pleasant, right?
Well, I think we'll let you off the hook for today. So I'm glad I heard it.